Welcome back. We'll continue with our development of the finite element method for these linear parabolic problems in 3 dimensions where we have a single scalar unknown. What we've managed to do in the last couple of segments is starting from the weak form, we've written out the starting from the strong form, we've written out the weak form and arrived as far as the matrix vector equations. Okay, and if you have your notes in front of you, you can go back and observe that the form of these final matrix vector equations was the following. Right, the matrix vector equations it takes on the following form. We have this new matrix, the mass matrix M d dot plus kd equals F. Now, in this form of the equations, we know that because of the variational methods we employ, the methods around the weak form, the boundary conditions are already embedded in this set of matrix equations. Right? What we do need to account for, however, is the initial condition. Okay, so whereas we have this linear system of equations, right? Essentially, a first order ODE, right? So this is a first order ODE. ODE being ordinary differential equation, so let me write that out. Right, in our vector unknown D. Okay, now because we've dealt with all this business about number of nodes in the problem and the number of Dirichlet boundary conditions and so on, I'm going to, as we proceed from here on, just say that D is a vector living in an NDF dimensional space, right? NDF is simply number of degrees of freedom. Okay, so those are the number of degrees of freedom NDF is the number of degrees of freedom we're actually solving for. Now, this is the first order ODE, and what that implies is that we do need an initial condition, which is something we had stated in the strong form of the problem. We just need to incorporate it here, and that ODE that we are working with is the following. Sorry, that initial condition that we need to work with is the following. D at time t equals 0 equals the vector of conditions which are obtained by taking u naught at the particular location of the corresponding node. Okay? And this is all the way down to u naught at x, now written as NDF. Okay? Right, instead of continuing to number by nodes, we've forgotten all about nodes. Now we're just looking at this linear system of equations where D is in R, belongs to an NDF Euclidean space. And this is what we have for the initial condition, right? It's convenient sometimes to also often to refer to this vector as just D naught. Okay? Right. So this is the setting we have. One thing I should mention is that whereas we sort of carried through our development of the method by considering a consistent mass matrix, one can also do global lumping. Okay, so a globally lumped matrix, lumped mass matrix, right? Let's denote it as M sub L for lumped, okay? It can be defined as, this thing can be defined, okay? And the way we do that is to simply say that M AB lumped is equal to the sum over C of M AC, okay? If A equals B, right? And it is equal to 0 otherwise. All right? Okay, and in some cases the problem is often solved with the globally lumped mass matrix. Okay, so this is what we needed to complete from the previous from the work we'd set out in the previous segment. We'll move on from here and begin looking at the integration algorithms for this class of problems. Okay, and this is going to depend upon time discretization. Okay, the reason for it is that the form of the matrix vector equation we're working with is what we call a semi-discrete formulation, and I explained why it is semi-discrete because we've gone through the discretization in space but not yet in time. Okay, so now we do time discretization. Now, in a move that may seem a little disappointing to some of you, the time discretization for this sort of problem is done with finite difference methods. Okay? However, the nature, the structure of the matrices M, K, and the vector F depend upon the finite element method. So even though we're going to use finite difference methods in this series of lectures for integration of time-dependent equations, those methods do continue to be affected by the underlying finite element formulation for the spatial part of the PDE. Okay, so this part is going to be finite difference. Finite difference methods. Okay, that's what we're going to use. Now I'll make a remark here, which is that a fully space-time Galerkin finite element method does exist. Okay, so space-time finite element methods do exist. And they have remarkably good properties as well. These types of methods are based on carrying out integration over omega and over the interval 0, t. Okay, so these are based actually on a formulation which is now going to look well, I probably shouldn't begin writing this formulation because one will get sucked into the rest of the development. But anyway, they're based upon integrating over omega and over the time interval, and they tend to have very good properties. For instance, they have properties of the type where the accuracy with respect to time is of higher order than what we will be developing here. Right? Accuracy is of higher order than with finite difference methods, FD for finite difference. They do come with a they do come at a cost, though. In particular, one has to develop a finite element mesh over space and time, and this can pose a challenge when one is doing problems that are 3D in space, right? Because then you have a fourth dimension in time, which can get to be a bit of a challenge to visualize, definitely. At any rate, the methods exist and they're actually very sophisticated. Okay, so we'll get back now to our finite difference methods, right? So the nature of the time discretization that we are seeking to carry out is the following. We are going to divide our time interval into subintervals. So divide our time interval 0, t into subintervals. Okay, and these subintervals are 0, well, let me do it this way. These subintervals are t0 to t1, t1 to t2, so on until we come finally to t n minus 1 to t n. Okay, so we have all of these subintervals, and what we also imply here, of course, is that t0 or t0 is equal to 0 and tn equals capital T. Okay, so if you look at this, what we've implied is that we've divided our total time interval into capital N subintervals, right? So clearly here we have n subintervals okay. The basis of the methods that we will develop is the following. Okay, so what we are going to do here is consider an interval t sub little n to t sub n plus 1. Okay, right, where of course little n belongs to the integer interval 1 to n minus 1, sorry, 0 to n minus 1. Okay, so we consider an interval of this type. The whole basis of our methods is going to be what is sometimes called time stepping. Okay, so time stepping implies right? Time stepping implies that we know the solution at Tn and we want to get to Tn plus 1. Okay, so time stepping essentially is the following. Knowing the solution at T sub n, find it at T n plus 1. Okay, right? So we're really sort of hopping along in time. Okay, so if you think about it as follows, That's the time axis, right? We've started here at 0. We want to get as far as t, right? We have t0, t1, right? We have tn, and we have tn, t little n plus 1, and here of course we have t capital N. Okay, so the whole idea is that, well, I know I know everything at tn. How do I get to tn plus 1? Okay, in order to proceed, and also actually in order to later on carry out some analysis, we need to lay down some more notation. Okay, and here is what we will do. So, some more notation. Okay, when I write d at some time tn, what I imply by this notation is the solution vector d if one were able to do exact integration in time. Okay, so this is the time exact solution, or the time continuous solution, shall we say. Right, at time at t equals tn. I am going to stick with the term time exact, sorry. Time continuous gets a little more ambiguous. The time exact solution. Okay, and this simply means if we were able to integrate our ODE exactly, right? This is our matrix vector ODE. Right, if we were this with initial conditions. If we had a method to exactly integrate this, then the solution that we would get at a given time tn would be this. Okay. In contrast, I will use d sub n, okay, to denote the algorithmic solution at tn. Okay, so this is the algorithmic solution, okay, by which we mean the solution that's obtained by applying some sort of discretized time integration algorithm based upon the discretization that we've just spoken of, right? The algorithmic solution obtained by a method to integrate the discretized, the time discretized ODE. Okay. All right. So we have this notation. What we need to do is actually, first of all, say what we mean by the time discretized ODE. And here's what we mean. Okay. Now, if I were to simply write out our ODE in the time exact form, here's what I would write it as m, just as I have it up there, but let me explicitly put in the time. Okay, supposing we were looking at it at time tn. Okay, so this would be md dot at time tn plus k d at time tn equals f, which potentially could also depend upon time. All right. Now, when we go to a time discretized version of this ODE, what we will write here is the following. We will write this out in the canonical form m Now, instead of d dot at Tn, we will adopt the notation that, well, if d is our solution, we can think of d dot as sort of the velocity of the solution, right? Just as a term, it's really just the rate of the solution, but we use the sort of canonical or the generalized term velocity for a rate here. And so we would write this as v, okay, indicating a velocity. Now, this is not a time exact quantity, so we are going to denote it as v sub n, okay, using this sort of idea. Okay, plus k d n equals f at n. Okay, this is what we mean by saying that, well, here v at n is a discretized approximation it's a time-discretized approximation again. It's a time-discretized approximation of d dot. Right? dn is, of course, just as we've defined above. Okay? So this is what we call, what I will refer to as the discretized version of the ODE. Okay? So this is the time-discretized or the time-discrete ODE. All right. Okay.